be presenting on my master's research that I've been working on for about the past year here at SLAB on optimal three-body trajectories for distributed telescopes. So just a roadmap for the presentation. First, I'll talk about the motivation in leveraging the circular restricted three-body problem. Then I'll give some background on key concepts. Then I'll go into the state of the art. And then I'll talk about my new contributions to build on and add to that state of the art work in the field. And then I'll summarize and offer some next steps. So why research the three-body problem? Oh, simply because it can allow for creative and complex trajectories that offer benefits that aren't always available with traditional two-body Kepler and orbit design. However, there's still a lot of work to be done in investigating three-body problem because it has highly nonlinear dynamics and chaotic behavior. So there's many opportunities still available to leverage the beneficial properties of three-body orbits, such as halo orbits. One such opportunity potentially would be the ORCAS mission, which is under development at Goddard Space Flight Center. So an ORCAS stands for Orbiting Configurable Artificial Star, and that would provide an artificial guide star, which would inertially align in a astrostationary orbit with a ground telescope and a target star. And the goal of this is to enable the use of adaptive optics in order to enhance the images captured by those ground telescopes. So in all likelihood, it will use an elliptical orbit for the actual mission, but other orbit types have been considered over the course of the orbit design, including halo orbits, which is why it's relevant. And this work could also have applications for other similar SLAB or Goddard related concepts, such as the Earth orbiting star shade, which is a similar mission, except that the artificial guide star is replaced by a star shade. These are just some requirements of ORCAS that may be out of date by now, but these are what I started with and what are guided my research. And they include, most importantly, the requirements about astrostationary orbits and remaining within the telescope's field of view and simultaneously aligned with the target star for a specified period of time. So this brings me to my problem statement, which is actually a dual statement. It's first, how can we transfer between halo orbits at the optimal cost over the course of a mission's lifetime, and while also viewing the most targets possible along each orbit. So just some quick background on the three-body problem itself. It deals with two primary masses. In this case, we'll be using the sun and the earth. And then one particle, which is a spacecraft, which is, and that third mass is neglected. And you can see on the right, you see the equations of motion, and they're nonlinear due to the pseudopotential term U on the right-hand side, which makes them difficult to solve. Well, they have no closed form solution. But one of the benefits of the three-body problem is when you use that problem formulation is it reveals the existence of libration points, which are these equilibrium points in the synodic rotating frame. And the L1 and L2 points in particular, which are seen on this image, are the ones most commonly considered for space exploration applications. And in this case of my work, I'll be using the L2 point. And one notable quantity, just to quickly covers the Jacobi constant, which is a scalar of the effective orbital energy of a particle in the three-body problem, and that'll come up later. Another key concept is halo orbit family. So there's clusters of halo orbits that form about each Lagrange point. So at this presentation, we'll be looking at transferring between halo orbits within that the same family. And one last concept, background concept, is invariant manifolds. So these spiral off towards or away from halo orbits naturally due to the dynamics and can be used to generate zero cost trajectories because they can, a spacecraft can divert on but just by a small perturbation. And this image shows the manifold tubes emanating from two halo orbits. The green is a stable manifold tube where all those different trajectories are spiraling towards the halo orbit, and the red is the opposite, it's unstable manifold tube. All those trajectories are taking you away from the halo orbit. So that background knowledge covered, we'll now delve into the state of the art. As I mentioned, Goddard and Slab had collaborated on ORCAS and explored halo orbits as a possibility. They did design halo orbits that met the requirements for the ORCAS mission to observe a single target star, and also noted that halo orbits would offer more potential in viewing multiple target stars and could reduce the fuel cost. So they could offer many benefits even if they wouldn't be used immediately. There's been some work done on halo to halo transfers. Johnson and Howell, as well as separately Gomez, developed different methods to switch between orbits in the same family. And also there's been work done not to transfer between the same family, but to transfer between different libration points or from bodies such as Earth to the libration point using both invariant manifolds and shooting methods. Then another important method to cover is modal constant decomposition. There's modal constants and integration constants are used interchangeably, but I'm going to use modal constants just to avoid confusion with other acronyms. But so in SLAB, Gafanti published work on using integration constants as state variables and showed how the variation parameters of method can be generalized and used for applications such as relative orbital motion, multi-agent control. And similarly, Burnett at UC Boulder applied a similar concept to, again, relative orbital motion as well as relative three-body orbital motion. But neither one applied it to absolute three-body motion, which is the focus of my work. And both also, first Gafanti, then Burnett, used the same impulsive optimization algorithm to determine minimal cost trajectories in MC space. So now I'll get into my own contributions. I had some initial attempts to find transfers that using invariant manifolds, then manual iterations, single shooting methods, and constrained optimization that had some pros and cons. But the most fruitful work I did was adapting that modal constants process that I just mentioned. So there's four main steps. One's to first, we separate the non-integral differential equation, so something like the three-body equations of motion, into an integrable and perturbative part. Second, we derive fundamental modal solutions to map the modal constants to the original variables and make the modal constants our new state variables. Then we can incorporate control maneuvers as perturbations and solve for an optimal control path in MC space. So this illustrates that first point where we take a differential equation and separate it into its integrable and non-integrable parts. And then the constants themselves will vary over time according to the non-integrable or perturbative part, which is this is the ICV equation shown there. So in order to create that separation in the three-body problem, we have to linearize the CR3BP equations. And we do that using a Legendre polynomial expansion. This is a similar method Richardson used to construct analytical approximations of halo orbits. So if you see on the right box, what we have on the left, we've extracted the linear terms from the equations of motion. And the right-hand side, that summation contains higher order nonlinear terms that remain. And so this shows that the same thing just in a matrix form. I'd like to take just a quick detour to just show the relationship between the three-body motion and relative orbital motion. And so you can note they're not the same, but there's many similarities between the two sets of equations once linearized. And this shows how we can apply control methods and different algorithms that have been used in one case to the other. So then once we have that, we can decompose the motion into a weighted sum of fundamental solutions by solving the eigenvalue problem of the plant matrix. So we find our fundamental solution matrix psi, and we have our state variables are now the modal constants, which is the vector, capital C vector there. And there's 6 eigenvalues, 2 imaginary pairs and 1 real pair. And those become the eigenfrequency. So we have one center mode related to the XY motion. We have divergent modes also in the XY plane. And we have center modes related to the Z motion, and those are decoupled. And the key, so this shows how we can map the initial conditions just by setting time to 0. But the really key power of the modal constants is shown here, where we can basically switch off those exponential modes by just setting the corresponding modal constants equal to 0, so that we can form periodic orbits that stay closed. And here, this gives some geometrical interpretation of the modal constants, where I've eliminated the exponential terms under the assumption I just stated, and rewritten the equations in phase amplitude form. So you can see how the modal constants correspond to the amplitudes of the in the x direction and the z direction, as well as the y direction. In the y direction, the amplitude is related to the x amplitude by a ratio derived from the eigenvectors of the problem. So now we can incorporate control by adding it as a perturbative term. And then going forward, if we neglect the non-integral part of the equations of motion just to simplify it and model it more efficiently, then the modal constants will vary solely under the influence of control inputs, which allows us to use an impulsive optimization algorithm based on the principle that each halo orbit will have its own set of modal constants. And so if we want to bridge the gap in the distance between those two sets of modal constants, we can do that using the control inputs while still minimizing our total delta V cost. And so the optimization algorithm is grounded in reachable set theory, where we have 2 convex sets and this is the optimization algorithm that I referred to that Gafanti and Burnett had both used in their works. So this is based on reachable set theory. We have 2 convex sets, one for the control inputs and one for the MC variations, all based on the cost J. And that yields this equation on the right for the minimum cost J, which is a function of the variable eta, which eta is a dual variable, which is related to the integration constant variation equations, and it's also it's a normal vector to the convex set C at the point where the goal MC change is found. So the impulsive optimization algorithm itself has 4 steps. First, to solve for that optimal value of that variable eta. Then we can solve for the maneuver times, then the direction of each impulse, and then finally the magnitude of each impulse. So we solve for eta using the optimization setup below, I used a CVX solver for this. And then the remaining steps can just be solved linearly. You don't need optimization software. And as I said, we solve for the times, then the direction, and then the magnitude. And we end up with the different maneuvers we need to change between halo orbits. So here's just an example of how that would play out, where we have two sets of modal constants. We define a control interval, and we can get the maneuver times and the maneuver cost and sum it all up after using the solver. Here's what that trajectory looks like. You can see the initial halo orbit, the target halo orbit, and the legs of the transfer trajectory in between, connecting them. So now, putting the modal constants work on the back burner for a minute, I'm going to talk about another thing I developed, which is a lower method to find the lower and upper bounds using that Jacobi constant I mentioned earlier. The Jacobi constant, each halo orbit has its own Jacobi constant, has its own effective orbital energy, and you can derive upper and lower bounds for the cost to switch between the halo orbits based on that unique characteristic. And here I ran several halo orbit transfers through the solver, the modal constant solver algorithm, as well as the Jacobi bounce method. And you can see how the solver, number one, the solver is within the bounds and is closer, much closer to the lower bounds. So it is doing its job to find a near optimal cost. And also, the more importantly, though, they follow the same trend, which shows how the lower bound can be used to sequence orbits, even if it won't find the exact magnitude. And then moving on to a different topic, which is the second part of the problem statement I defined earlier, which is to view multiple targets on a single orbit. I basically did this by generating a grid search based on the different parameters for halo orbits, their position, and also the time, the epoch time that the orbit would start, since we're dealing with the inertial frame now when we're talking about viewing targets. And I refined the mesh of that grid until it produced an optimal answer. So this is an example of that, where we have the heat map grid on the right. We're trying to find which orbit views the most targets, and on the on the left, and then on the right, you can see plotted in the viewing plane with declination, right ascension. The inertial target stars are in blue, and the spacecraft path, which is the most optimal, takes it through coinciding with those target stars. And now finally, this is something that's I've only done recently, so I'm still figuring out some of the kinks, but I've tried to consolidate all this and combine it into a multi-orbit trajectory optimization for the whole lifetime of a mission like ORCAS. So in this work, you would find 3 halo orbits that align with the most target stars using that grid search algorithm I just described. Then you can use the Jacobi bounce constant method to determine the cost optimal order of that orbit series. And then if you move into MC space, you can calculate the optimal transfer trajectories using the impulsive solver algorithm I described earlier. And so here's an example of how that played out, where you see we have the three oval halo orbits and 2 transfer trajectories in between them, bridging them. This is in the synodic frame, and you can see the same trajectory expressed in the inertial frame, with Earth at the very center there. This is the ECI frame. And then finally, in the viewing plane, you can, with right ascension and declination, these are the halo orbits plotted on there. Like I said, I'm still working out some of the kinks of this method, so there's, which is why the transfers aren't plotted on here as well. But overall, it holds a lot of promise for just putting together a fully combined trajectory. So to wrap up and summarize this, shown how the CR3BP orbits could be promising, especially for projects like ORCAS, and be able to demonstrate how modal decomposition and grid search and the Jacobi bounds can all be combined together to create an optimal multi-orbit trajectory that can find which orbits view the most targets and the optimal way to transfer between Hale orbits. And of course, this shows how algorithms designed originally for relative motion can be applied to the circular restricted three-body problem and potentially vice versa. And finally, next steps, just want to incorporate some more complexity. As you know, I made a lot of assumptions that I stated throughout. So taking those into account instead of oversimplifying the problem would be the good next step, as well as deriving more physical meaning in for the CR3BP modal constants similar to relative and Keplerian orbital elements. And finally, I'd like to also incorporate more of the actual ORCAS requirements in terms of viewing time and other conditions to make sure that the orbits are actually astrostationary and more realistically fulfilling the mission objectives. So that's the end of my presentation, and I'll take any questions that you have now.